Okay, very good. So hi everyone. Let's continue. So I think last thing we did in the last lecture was we introduced this class of symbols of order Sm and the corresponding pseudo-differential operators, right? So there are two things: symbols and then operators. So let us recall then. So this is symbols of order m, which could be any real number really. So the class was Sm. So we said that A, which is a really function of two variables, belongs to Sm. If first of all this A of x and c goes from Rn plus Rn. So maybe I should say this is Sm of Rn. Symbol of order m on Rn. This is smooth plus compact support in X. This is just a technicality which we will get away from these sort of technicalities when we go to compact manifolds soon. Smooth plus compact support in X. And so the second one was this growth condition that differentiating. So yeah, for any alpha and beta, there exists some constant C alpha beta such that absolute value of d alpha x, d beta c of A of x and c.
Did you need it to be smooth for R2 and or when you restrict to each R and you need it? I think last time you mentioned you restrict. I think you said when you fix one coordinate, another coordinate.
No, it's jointly smooth. I mean, yeah, I don't think that really matters right now. I think it's not. But I think jointly smooth is safe enough. Yeah. For any alpha and beta, it's constant such that this is less than equal to C alpha beta, absolute value of 1 plus C to the power n minus beta, right? So that was, so that's estimate growth condition in terms of C, which kind of informally tells us that this guy is of order m in C. Essentially, it's of order m C, and then we define this differential operator or pseudo-differential operator attached to this. This is going to be kind of an operator that differentiates of order m plus other things, but essentially that's right. Okay, so that's these are the technical conditions for this, and then for this A belongs to Sm. We attached an operator A, so this is called pseudo-differential operator. So I just write pseudo of order m. So this operator actually really goes from Hs of Rn to Hs minus m of Rn. Similar to the situation for differential operators of order n, that we were able to extend them to subgroup spaces. So this is defined by A f x equal to integral over Rn e to the I x dot c, and then the symbol A x C and Fourier transform f at C and then dx. So it's like the formula that we saw for differential operators. You Fourier transform, multiply by the symbol, and take Fourier transform back. So that's the trick that allows, if you go to Fourier mode, you can talk about some operations that don't have obvious manifestations in position space. But in momentum space, for Fourier mode, they have this nice incarnations, which is really cool. Okay, so, well, I mean, you can start with, for example, Schwartz function class, and then you're doing the estimate, using this estimate, you notice that it works and extends here. Okay, so that's it. And we're going to define a kind of equivalence relation on symbols, and then a corresponding equivalence relation on differential operators. That's going to be very helpful for us. So, okay, so let's move on to. So, symbol A is, for two symbols A and B, we call them equivalent if a difference is a symbol of order m for any m, basically. Yeah. If A minus B belongs to Sm for all m. And of course, you notice that the emphasis here is for negative m's. That matters, right? So it follows that then the corresponding pseudo-differential operators A minus B has the property that this actually goes from Hs by using that thing we observed to Hs prime for all Sms prime. So it follows that if we just take, let S prime go to minus infinity, this is really an infinitely smoothing operator using Sobolov's lemma. Yeah, using Sobolov's lemma. It follows that A minus B actually maps Hs to C infinity of Rn. So notice this is a very strong condition on an operator. Right now we are sending any kind of non-smooth, even distributional type objects by this operator into smooth functions, infinitely differentiable functions. So this is a very, very, very strong condition that if you have the difference to be in Sm, so such operators are called infinitely smoothing. So they are smoothing operators. They are much better than integration operators and this sort of thing. They're infinitely smoothing operators. So this is called infinitely smoothing. So that's that. Now, what can we do with this?
Can you give us a specific example?
Sorry?
Can you give us a specific example?
Yes. We'll see examples. Yeah. I mean, you can take a symbol which is of the form e to the minus, for example, absolute value of c squared, or e to the minus c squared, for example. An operator, and then put something like compact support in front, and then times exponential of minus c squared. This is an infinitely smoothing operator. Yeah. So, but we will have more. In fact, we. Yeah.
Okay. I have a question on that. So
Yes.
this equivalence relation on symbols,
Yes.
what does it translate to for the pseudo-differential operators?
So the exactly that's the thing, and we just say two pseudo-differential operators are equal if their inverse, if their difference is an infinitely small thing in this sense.
No, but what does it mean in terms of pseudo-differential operator itself?
In terms of you mean symbols. In terms of pseudo-differential operators, really means this. In terms of symbols, originally means this, but actually I'm going to relax this and get some condition that's going to be very useful to work with. Yeah. All right, so now we just say definition is that we just say a symbol A is equivalent to infinite sum like this, j from 0 to infinity, if for any m positive there exists n such that A minus sum aj, j from 0 up to n, this actually belongs to S minus m for all n bigger than equal to. So the whole point of this definition is to make sense of this notation. This concept. You see, one of the things that we have to be aware here is that this is not a summation. This is not a usual summation. I mean, we are not assuming that this series is summable in any sense. We are not summing the series. That's a notation. It's asymptotic equivalence of these functions in the sense that if you cut at any stage, the difference with finite sum, of course this is now finite sum, is going to be in S minus n. So what does it mean? It means that as we go further in the series, the difference becomes more and more smoothing operators. It becomes more and more regular. So in some sense, we are replacing this by its kind of asymptotically equivalent symbol. But the point of writing in this form is that we can bring in algebra. Well, we could not bring algebra for these things if they are not differential operators. But here we're going to work algebraically. So this is a very important concept. I mean, this is equivalence of this with this symbol. So you have to get used to that concept. Okay. So now there are two results which are very important. Actually, makes the whole machine work, and they are. I mean, the proof becomes technical, but it's really, I believe it's just like this rule. But let me write the result and then make some comments. I'm not going to prove it, so let me just. So what's the best way to prove this? Yeah. So let P and Q belong to pseudos. Okay, I will define that concept. Then PQ and P star are both in okay, with symbol of PQ asymptotically can be given by sum 1 over alpha factorial, alpha from 0 up to infinity. I believe I should put D usual partial derivative with respect to C of P and with I partial derivative with respect to x of q, that's that one, and symbol of p star asymptotically is given by sum of from 0 to infinity 1 over alpha factorial d alpha c and then d alpha x p conjugate. That's it. So in these formulas where p, of course, little p is the symbol of the operator cap P, right? Is the symbol of this operator capital P, and little q is the symbol, that the way that we define, right? That operator. For example, this is a symbol of order m. This is a symbol of order n prime, and they. Now this P star, how do they define P star? So P star can be uniquely defined if we just use L2 norms on functions. This fixes P star. And P star is fixed by the usual, adjoint condition, fixed by, so let me write it, I hope it can be. Let me write it like this. P star is fixed by inner product of maybe P of F and G. So this is L2. This is equal to F star G of 2. At least for Shor's class functions, this makes sense. Now, what is K? K inside Rn is a compact set. And pseudo K is the restriction of this. The pseudos are Rn to functions with support in that compact set. We just fix a compact set and work in that compact set in order to make all integrals convergent, actually. Compact set and pseudo K equal to pseudos on Rn restricted. Okay. Again, there is some technicalities about support of things here, which are unavoidable because we are on a non-compact space, and so things can diverge. So we have to. Okay, so now the way to see this is the following. Of course, PQ, it's not obvious that this is going to be, because these are not differential operators anymore. If P and Q were differential operators, then all you need is just calculus to show that PQ is a differential operator and its symbol, full symbol, is given by equality, and this sum would be finite. Is the sum, for example, differential operator of order m and n prime, this sum would be n plus n prime term or something like that. So that would be finite. And this is also, we checked in some cases last time, and actually this. But here, we are making a bigger claim. PQ, which is defined as compositions, is again a differential operator of order m plus n prime, pseudo of order m plus n prime. And we don't have access to its exact symbol. But asymptotically, you know something. This is not the symbol of this guy. This is just an asymptotic expression. Two functions can be asymptotically equal without being equal at all, like Taylor expansion. But that's good enough for calculation, and that's also good enough for calculation. So proofs of this, I invite you to look at, for example, Gilkey's book. That's the best source, really. And I follow Gilkey in many places, anyhow. So it really is going to take about 2 hours to give all the details of this. So I better spend time on it.
Would it be
Yes.
sufficient for little p to just be asymptotically equivalent to the symbol?
That's also, I think, yes, I would guess that also works. Oh, you mean efficient?
Sufficient. Like
Oh, sufficient. Oh, yes.
P is asymptotic to symbol
But that's-
P in the formula.
That's a good point. I believe so. I believe so. Yes, I believe that. In fact, yes, I think. Because everything is asymptotic, I think this carries over. I'm almost sure about that, but so you check it when you look at the reference. Okay, excellent. So we have that. Now let's see what we can use with this. Now you remember we defined a notion of elliptic differential operator, which is just an algebraic expression, differential operator defined elliptic. Now we are going to extend that concept to elliptic pseudo-differential operators and elliptic symbols. We need that too. So this is a concept we need. It's called elliptic symbols. So a symbol AXC belonging to Sn is called elliptic if, first of all, this should be invertible for large C, not for C different from 0, for large C. If AXC is different from 0 for all x and for all C very large. And in that range then, where this is invertible, by invertible we mean as a number, of course it's non-zero number, because these are honest functions. -1, so its absolute value, we want to be less than equal to C times 1 plus C to the power minus 10, again for C large. That's the technical condition that we want. If these two are satisfied, then this is called an elliptic symbol. And the corresponding differential operator we call elliptic pseudo-differential operator. Okay? Okay, good. Any question? Okay, so the first thing we have to check is that, in fact, this concept is not in contradiction with our old definition. So we have to check something. Check. So this would be an example. So let sigma x c be just sigma, you know, a what was our notation? A alpha x. I mean, yeah, c alpha. Absolute value of alpha less than equal to n. Right? So m is an integer now, and okay, of course this belongs to Sn. This symbol belongs to Sn. Now it's very easy, in fact, to see that this is elliptic. Sn, so sigma is elliptic in this sense that we defined over there. You can only its leading symbol is non-zero for all c different from 0. If I only sum a of x, c alpha, absolute value of alpha. So this was the principal symbol, right? Is different from 0 for all c different. So this was our old definition of ellipticity, right? So the two definitions are not in contradiction to each other. So this was old definition. Some kind of relevant examples in this kind of guys is when you look at Laplacian and Riemannian manifolds, right? So if you have a Riemannian manifold, any questions or comments? Okay. So this would be another example. G, Riemannian manifold. Then a Laplacian in local coordinates can be written as, so let me recall, I guess I very briefly touched on Laplacian. So Laplacian on functions, for example, was like this, right? Anyhow, in general, Laplacian was like this, d plus d star squared. This is equal to d star d plus d star. Now, these scalar Laplacians, and in local coordinates. So you can prove a lemma to show that Laplacian is given by actually 1 over root g di, I believe, yes, that's, we have to do two partial derivatives, but we have to remember how. Root g, gij, and then dj, right? So here is summation over repeated indices understood. So Einstein summation understood. Okay, so what is this G? G is determinant of Gij. And, oh, sorry, this is in contradiction with this symbol over here. But here is, this is Riemannian metric, but this is the volume component of volume 4. This is determinant of Gij. Written in that local code. Now, this operator is also, I mean, this is a differential operator. It's not even, it's not pseudo, it's a differential operator. This is also elliptic. Well, I mean, we have seen a proof I guess we have seen a proof before, but let me give a proof using this sort of leading symbol ideas, to exercise a little bit with this. So just to do that, I mean, it's very easy. You can notice that this is given by local coordinates by the following formula. So in local coordinates, delta.
So just to clarify, G upper ij is the inverse of J.
Beg your pardon?
G upper ij is the inverse of G.
Yeah, that's the inverse. Yeah, that's the inverse. Exactly. So now this, if you do this calculation, it turns out that this delta Laplacian is equal to Gij, di, dj, plus some lower order terms. So there's a first order term, which is a k dk plus some constant b. Well, I mean, constant is a constant function locally. I mean, these functions are not globally defined. I mean, these are just local. Anyhow, they is based on that. So, of course, this thing you notice that. So, the symbol of this, so principal symbol, is minus Ij, Ci, Cj. So it's a quadratic form, but this quadratic form is positive definite. The minus is negative definite anyhow. So this is different from 0 for all C different forms. So this guy is elliptic again. We have seen a different proof before, but this is more down to earth proof. Okay. So, any questions?
Is it easy to see that elliptic makes sense in context of the equivalence? Like, if an operator is elliptic, equivalent operators will also be.
Yes, yeah, because the correction term is going to be of very, very low orders, and at infinity, that order, order m is the leading contribution. So, yeah, that's not, yeah, that's it. Yeah,
Can you give us an example of like a non-elliptic operator that is like non-differential operator that is
that's elliptic. Yeah, okay, so yes, I mean, that's very easy. I mean, just construct something like this. I mean, take this symbol. All you have to do is just symbols, right? So take this symbol, A of, actually we looked at this symbol before, equal to A of x, I mean, just alpha of x, divided by 1 plus absolute value of c squared to some, any power if you want, even this.
So is there an example that naturally arises in geometry? Like for example, the Laplacian or the del bar naturally arise in geometry. Is there an example from geometry that's
right? So examples that appear in geometry, as far as I know, most of them is geometric differential operators are really differential operators. So we need this pseudo stuff just to invert them. That's as we'll see right now. I mean, the next step.
So, for example, if I have a non-integrable almost complex structure,
What is it?
a non-integrable almost complex structure.
Yes.
And if I look at the corresponding del bar for that non-integrable case, will that be a sort of
No, that's differential operators.
that is still a different?
Well, that's a differential because I mean it's del bar anyhow. You are differentiating.
Well, it's a non-linear PDE.
It's a well, okay, so nonlinear PDE goes in a different direction completely.
But that does not.
Well, I mean, this is a linear approximation to that theory. So if you have a nonlinear PDE, like Yang-Mills equations, for example, over Riemannian manifold, yeah, they are nonlinear elliptic PDEs.
Right.
Yeah, and then to use this theory, you have to work on the tangent space to space of solutions and all these things.
But that is not a magical plus.
No. These are very much a linear theory. I mean, all our PDEs are linear. Right. I mean, for example, this is elliptic symbol. If A is non-zero.
There is no nice geometric example.
No, I'm just thinking about this sort of Yamabe operators, but they are also some powers of Laplacian or something like that. I don't think they are nice. I don't want to say 100% no, because that's dangerous. But probably all operators that are of importance in geometric operators are Dirac operators, Laplacians, Dolbeault. I mean, yeah. I mean, essentially, they're all born out of Dirac operators. Essentially, they are D star D or D. Okay, but now the main thing we want to do today is to show that Actually, elliptic PDEs can be inverted modulo smoothing operators and all these things. Again, notation is a bit awkward in this non-compact case, but we have to do that, and then next week we'll go over manifolds, and then things become much more. But we have to do this in order to do the manifold case, unfortunately. Okay, so this is the theorem. So this is inversion of elliptic operators. I mean, I just gave you the name, but this is the temporary name of this. So if P is an elliptic operator, then there exists a pseudo-differential operator Q such that PQ minus, I mean, PQ is equivalent to I in the sense that the difference is an infinitely smoothing operator, and also QP is asymptotically equivalent to identity. That's also infinitely smooth. I.e., so this really means symbol of PQ is asymptotically equal to 1, and symbol of QP is also asymptotically equal. Okay, so we can invert it modulo smoothing operators, or we can invert the symbols modulo infinitely smoothing symbols, if you want to work with symbols. Now, can you tell me a situation? Oh, I have to connect my file. Can you tell me a situation where we did something similar in a more abstract context?
Well, it's reminiscent of inversion modular compacts.
Yes, that's absolutely true. That's reminiscent of Atkinson's theorem, right?
Yeah.
We said that an operator, Atkinson's theorem said that an operator is Fred whole if and only if it is invertible modulo compact operator. So indeed, we showed that if there is something inverse point. And these infinitely smoothing operators over compact manifolds, indeed, they are going to be compact operators. So if you believe this by patching together going over compact manifolds, then we have proved that any elliptic operator defines a Fredholm operator. But okay, we have to use the right kind of Sobolev space context. But then over C infinity turns out to be actually also a Fredholm operator in algebraic sense. That also follows. So that brings us back to the very first lecture. So these elliptic PDEs are the main examples. So we have to prove this result. So, okay, good. So proof. Any questions?
And the statement given elliptic pseudodifferential.
Yeah.
Are different.
Yes, that's what pseudo is. It's just defined by some symbol of some order n. That's all. Exactly. I'm not assuming it's a differential operator. I mean, it's a pseudo, really. Yeah. So proof. So I give the sketch, but really the main idea is here. I mean, all you have to fill in is very small amount. Okay, so let's let's pick some notation. Let P xc be equal to symbol of P, capital P, right? So because this guy, so I mean this for example belongs to Sn, right? So I mean we know that this guy is non-zero for large C, right? So Px C inverse exists for large C. So the first thing we are going to do is that, okay, we just take this for large C, in large momenta, basically. These large momentas are infrared domain. Large momenta, no, ultraviolet. They are ultraviolet because momenta are related to frequency. So this is really ultraviolet. So for ultraviolet domains, we just invert it. And but the inverse may not exist for small c. So what we do, we're gonna mend this function. So we multiply with a kind of bump function, which is near zero is 0, and at infinity is 1, and completely smooths this out. Okay. So take any sort of, I don't know, it's maybe bump function, yeah. So which is going to look like this. So this is 0 here, for example. I mean, by -1, 1, I mean sphere of radius 1, really, right? And here is 1. We can take a function which is like that. Okay? And then I'm going to multiply my my function by such a. So then I just say P x c inverse psi of x and c. So this is a smooth function now, right? This is a smooth function. And all we have to do is to check that actually I can replace now my inverse function by that one, okay, basically. So the statement is that, let's get the notation right. Okay, so I need, okay, so yeah, let's call this Q actually. Yes, let's call this Q of x and c. Then, easy, really easy to see that this guy, Q of x and c, is not quite the inverse of P, but is asymptotically inverse of P. X and c times P of x and c asymptotically equal to 1. So in other words, I can replace this sort of at bad points, which is only on a compact set, which is not invertible, by some function which is smooth out this singularity at 0 and near 0, perhaps at 0, by this good function. And then I don't have equality equal to 1, but then I can have this. That's easy to check because these asymptotic relations to be in S minus m's has to do with infinity. And at infinity, you're fine. Infinity, you have inverted it. At finite lengths, I mean, that's not finite distance to 0. That's not. You can provide the analysis 1 estimate for this. Okay, so this is the first step. So I think that's related to your question, look also that now we are replacing the symbol by something which is equivalent. So in other words, now I'm going to say actually that maybe I can erase this part. So I can assume that actually the symbol of my operator is inverted. So I can assume without loss of generality that the symbol of my operator actually is different from 0 for all x and c. Okay, so now let's look for the inverse now. So we are looking for an expansion. So I'm going to call this, by the way, Q0 of the form Q of xc sum Qj xc j from 0 up to infinity of such symbols, right? Such that Qj belongs to Sm minus j, or rather S minus m minus j, for all j, and of course we want this product, we want the corresponding operators with -1 to be infinitely smoothing, so the products we want to be, so let me write it like this, P star, so this is this new product that we introduced of sum Qj, j from 0 up to infinity must be equal to 1. Star is the product of symbols that we introduced. It's the symbol product. Remember, we had a sum, infinite sum, asymptotically given by that equation.
Okay, so I'm a bit confused. Why aren't you done that? So isn't that what you promised to show, that sim?
No, this is just the usual product, but that's not, if you take the differential operators, that's not going to follow this rule. The composition of differential operators follows this star product here, which is that more complicated expression. And we have to solve it in that algebra, in this star product algebra kind of. Right? Okay. So, question? Okay. So now we have a formula, of course, for this star product. So let me write it. This P star sum Qj, j from 0 up to infinity, maybe I put I from 0 up to infinity, is equal to, if you use the formula that I wrote down, this is equal to sum j from 0 up to infinity, and then inside, this is going to be given by sum absolute value of alpha plus j equal to k, d alpha c of p d of capital D alpha x of q, of qj. This follows from the formula that we have. Now, this sum is finite. And of course, this was the definition that we used for star products. Okay, so now this equation, we want it to be equal to 1 now. Am I in the frame still? Okay. So then it means that the zeroth order, the first part has to be equal to 1 and all other terms have to be 0. So for k equal to 0, this equation, there should be 1 over alpha factorial as well. Sorry, should be 1 over alpha. Right, we had 1 over alpha factorial. So for k equal to 0, what we have is that p q0 should be equal to 1 on the nose, and by our fixing at, the first observation, we can assume that. We can assume that p is inverted. So this is doable by our first move. So that we can do. Now let's write the second equation. Let's take k equal to 1, because now it's a kind of iterative process. We have to show that there are infinite number of functions, q0, q1, q2, of the given orders, such that these things are always. So let's look at the next equation. So what is the next equation for k equal to 1? Okay, so we have this term d1p, right? Times dxc. Let me put it like this: dxcp times dx q0, right? Plus what kind of equation? dxcp dq0 plus pq1. That's the equation that we get. Now, p of course is known. q0 is also known. q0 is known. And now we are looking for q1. But q1 is solvable because I can just multiply by p inverse and solve it. So from here you get q1. q1 is you get q. Now, the structure of these equations are all like this. The thing that's known always appears as like qk or q whatever times some p, and then the other parts, the rest of the recursion, is just what is known. So this is always solvable. So let me just write it for k equal to 2, for example. What we get, we have 1/2, for example, d2 c of p d2 q0 plus d1 c p d1 q1 plus pq2. Again, as I said, this is solvable. So because this is known, this is known, this is known. Okay, so we can algebraically at first solve these equations, right? So that's fine. The only thing that remains now, we have to check that these the functions that we obtain actually have the right orders, because this is the orders is the one that gives us control, right, over the analysis, and that's not difficult. Okay, so with this choice, so let me write it like this. With this choice of q0, q1, q2. Sorry about that. With this choice of q0, q1, q2, etc., easy really to see that q J belongs to S minus N minus J by induction. I mean, of course, the first one we just chose, the way we chose, was the inverse of the symbol of order. I mean, the literal inverse of multiplication inverse of symbol of order n. So that's order minus n. And then you just use, I mean, the definition of symbol of order n. I mean, when we have something of order n, if you differentiate it, I mean, the order n drops by 1, becomes n minus 1. So there is something here, and then you get control. So I invite you to do this in detail, but I mean, that's easy. So I think that's end of my sketch. But the idea is really, we are solving an infinite number of equations with infinite unknowns, and this is solvable. And of course, it's not pure algebra because we have to care about analysis too. The analysis is fixed, I mean, it's taken care of by going through orders. I think this result is the most important result for everything we want to do, because it shows why we need the pseudodifferential operators. It shows these ideas of orders, these ideas of symbols, this star product that we use. All these things really come together in a very nice way in this result. So this is really crux of the matter. This is just think about it as much as you can. Any questions or comments?
Sort of like iterative differentials actually.
Pardon me?
This sort of iterative differential solving is actually it's essentially the crux of integrating solutions in differential.
Solutions of differential equations?
No, in deformation theory, when you have solutions
I believe it's related to that.
Yeah, to integrate a solution, you need to solve this exact set of iterative differential equations.
Yeah, okay. I mean, yeah, indeed, deformation theory, this star product is related to deformation theory in one form or the other. There are many different types of deformation theory, but essentially, yeah, this is.
Yeah, so in order.
Yeah. This is so this problem in a way is unobstructed. We can,
yeah, it's unobstructed. Yeah, because it's just linear at the linear level. Right?
Mm-hmm.
It's not on a manifold.
Yes. Well, I mean, on the manifold, I mean, we will move to manifolds also. But again, on the manifolds also, those differential operators are linear.
Okay.
Okay. So now, but let's derive some amazing consequences of this, which is quite surprising and shocking, actually, that one can do this sort of things. I mean, corollary 1. So we are going now to derive some regularity theorems that I promised. So corollary 1. So this is kind of first regularity theorem. Okay, so if P, okay, so if P is an elliptic pseudodifferential operator, and if Pf equal to 0, then F is a C infinity function. I mean, just to get a feeling for this, imagine you are dealing with a differential operator of order 2, for example, right? Which is elliptic, like Laplacian. And to talk about solutions of this, you normally assume that, okay, this is second times differential function, differentiable function, as in the kernel of Laplace. Now it's automatically infinitely times differential. Just being in the kernel of elliptic PDEs forces the function to be infinitely differential. So this is quite remarkable. Yes, for example, I will mention those. Yeah. So let me just give you the proof. There exists a Q such that QP minus identity belongs to infinity smoothing, right? Operator, right? Yes, we proved. Now we are a bit lax about domains of such things and things. So, but the idea is to give the main gist of the idea. So, if you want, you can be more precise and fix domains and all this. But essentially, what happens is that there exists an operator Q such that QP minus identity belongs to a smoothing operator. Since your class of functions which need not be infinitely differential function, for example, solar types into a smoothing operator. Now, then what happens? Then QP minus I times F. Of course, this is minus F, right? Well, I mean, this is infinitely smoothing, so this belongs to C infinity, right? Okay, so your F belongs to C infinity. That's it. So it looks like it's like a game now, but we worked hard. You know, we use Fourier theory, pseudodifferential inverting this. So, example, a C2 function that satisfies Laplacian of f equal to 0. So a harmonic function, right? For example, an Rn is automatically C infinity. Of course, we know even more is true. It's automatically analytic, even in Rn, when you don't have access to complex structures. We know a harmonic function is analytic even, but up to C infinity we can prove using general theorems, pseudodifferential operators. Okay, so another thing, when you take complex analysis, the first thing, if you paid attention, is the following very, very surprising fact that you have this function, right, f, defined on some open set, and you just assume that this complex differential exists. F prime of z exists at every point in this open set. I mean, f prime z is limit of f of z plus delta z minus. It's the usual. But then you go on and prove that, okay, this function is actually analytic, considered even as a real function in O2. This is mind-boggling. I mean, you don't have anything like that for real value functions, differentiable 2 times, n times differentiable on the real line. Of course, it's not going to be n plus 1 times differentiable automatically either. So that's quite surprising. So here's another example. Well, yeah, I mean the bar operator that's kind of related to what I was talking about. Yeah, 1/2 dx by dy. Del bar f equal to 0 implies that f is C infinity. In fact, both of these operators are elliptic, as we checked a long time ago or some time ago, and then this follows from this result. It would be good to see counterexamples of this, that when your operator is not elliptic, it could be functions that are in the kernel, but they are not C infinity. Let me give you an example of such. Do you remember any examples of such things? A differential operator whose kernel is not necessarily consisting of infinite differential functions.
Just take like differential operator delta x.
Sorry?
If we just take the differential operator and
Yeah, let me give you a kind of prototype of such things.
delta x square minus delta y square.
Yeah, the wave operator. Yeah. Perhaps any operator that's not elliptic, if you choose, you're going to see this phenomena. But let me give you a kind of prototype of such things. As the wave operators. So box is equal to d2 dx2 minus d2 dt2. Now box f equal to 0 does not imply that f is infinity. The symbol of box xc, well, I should say, yeah, I mean, what's the symbol of this operator?
Say 1 square minus
Is minus c1 squared and then plus c2 squared, right? The symbol of this guy. And this guy, its symbol vanishes completely on the light cone, right? This is c1, c2, so on the light cone you are 0. So it has a large singular support, so to speak. Anyhow, can you give me an example of a solution that's solution of the wave equation, but is not C infinity?
Basically, the equation solutions.
This problem, in fact, was solved by D'Alembert in 18th century. So D'Alembert, I mean, he wrote down, first of all, this wave equation. This is due to D'Alembert. That was the equation of vibrating strings and all that. So D'Alembert, I hope my writing is correct. I'm not sure. Is that correct?
1L.
1L?
And maybe A for the first E as well?
Here should be E.
I think so.
Or maybe D'Alembert. Oh, D'Alembert. Maybe this is. Maybe it's just D. There's no apostrophe. Let's check this. For any F belonging to C2 of R, so let me just put U belonging to C2 of R, F of X and T equal to U of X plus T is a solution. In fact, D'Alembert found the general solution of such things. For any U and V, I would say, then is plus U of X minus T. I mean, you can take linear combinations of these two things as a solution. So these are backward moving waves and these are forward moving waves, but okay, it's a solution. So easily you see that, of course, you can take some function which is in C2, but is not in C3. So you get a solution. So this was done by D'Alembert, actually. Is that, did you find that?
It wasn't E. Or I said it was E.
Oh, it should be E?
Yes.
Oh, correct. So then it's okay? Okay.
Yeah.
Very good, thank you. So, yes, okay, so this is a counterexample to ellipticity. Well, I mean, then it's not elliptic. I mean, it's very much related to these zeros on these things and a lot of other issues. Wave propagation and Huygens principle and all these things, but that's just. Is it Huygens? You say?
Huygens.
Huygens?
Yes.
There should be a,
Yeah.
like my last name. Huygens. Yes. He's a great guy. One of the greatest, yeah. Indeed. All right. He's the only person I think Newton mentions in his, maybe he's the only person Newton mentioned in his book on optics, I think. All right, so I think I want to just give one more regularity theorem, which is about range of such things, and then I think we are good for now. Okay. So this is a correlate 2. So we saw that the kernel of these elliptic PDEs consists of C infinity functions. Now, yeah, so one can indeed improve this result. In fact, if I think something like this is true, if P is elliptic and P of U belongs to C infinity, then U belongs to C infinity. I mean, we did the case where P of U is equal to 0, which is obviously in C infinity. Then we concluded that U is in C infinity, or F is. No, but here is a bit more general, right? So we are doing a bit more general case. So, but I believe proof should be the same because we have got QP minus I. So again, you just say there exists Q such that is infinitely smooth ring. Right? All right, so then what can we do? We can just write minus U is equal to QP minus I times, is that it? No, that's not correct.
Q also to be sending into C infinity.
Sorry?
You need Q also to be sending C infinity solutions to C infinity. Because P
that doesn't work, right? I mean, obviously,
yeah,
even this is not true, of course. I know that P of U, oh yeah, okay, okay.
Q sends C infinity to C infinity.
Then we are done. Yeah.
Then we are done, yeah.
What if I just use PQ minus identity? This is infinitely smooth thing. Does it help?
No, you don't know if Q, U is.
I don't know. So what can I do? What did I do here? I just take QP minus identity as before. It belongs to C infinity. Oh, yeah. Okay, so right. No. I mean, that's okay. So this we know that. Okay, so such that this guy. Oh no, I have already written that. So okay, so sorry. So okay, so there exists Q such that QP minus identity is infinitely smooth. This we know. Okay, so such that then maybe we can write like this. Then we have QP minus identity U. This belongs to C infinity, right? Because it sends anything into C infinity. So in particular, this one is also going into C. So, but this I can write Q, PU minus U. This belongs to C infinity. But this PU is infinitely smooth. This PU it belongs to C infinity. Of course, I mean this Q sends C infinity to C. Right? Just look at the formula. For any pseudodifferential operators, they send C infinity functions into C function. I mean, just look at the formula, because the formula is you're multiplying by a smooth AX, a smooth symbol, and you're inverting Fourier transform back. So this is sending a smooth interval. That's not a problem, right? So okay, so we are good. So this thing then belongs, so this part belongs to, in other words, this part we're saying belongs to C infinity. The difference is in C infinity, so it follows that U belongs to C. Okay. So it basically is similar idea. Right? I mean, the fact that pseudo sends, just look at the maybe, I mean, this is like A, F, right? X was integral e to the I x dot c, A x c, right? And then what was it? F hat c. Look, this is a smooth. I mean, if f is smooth, then this function is also smooth. So the whole thing is smooth, and this is good converging thing. So this stuff is fine, and okay, I think now we're good for today. So what we're going to do next is to look at to move everything over manifolds. That's not difficult. I mean, there is some step about moving pseudodifferential operators to manifolds. That's kind of technical, but it's done a long time ago, I guess by Zilli and others. And by Zilli mostly, I believe. And then once we have that, I think next week we can prove basic finiteness and regularity for elliptic PDEs on compact manifolds. And then after that, we have to move to getting Hodge decomposition and also getting results for elliptic complexes. But those are not very difficult. So we are now a good way towards getting the analysis out of the way, so to speak, and then. Any questions or comments?
Are convolutions examples of these infinitely smoothing operators?
Convolution operators?
Yeah, because that is almost,
so,
I think the formula there, it's almost, maybe it is actually a convolution of.
Yes, it is some sort of
that.
That they are. If the kernel is, I mean, if one function is infinite, is a smooth function, then that. Yeah. Yeah. Okay, so I just stopped the video then, and then we can just.